So far, we have learned what atoms and elements are, how to diagram atoms, how to group atoms together, and predict their properties based on their location on the periodic table. In this video, we will start to learn how and why atoms form chemical bonds. A chemical bond occurs when two atoms bond together to form a new substance with new properties. This new substance cannot be separated by physical means. That means using a filter, a magnet, or distillation will not separate the atoms. For example, sodium is a soft metal that reacts violently with water. Chlorine is a poisonous gas, but they combine to make sodium chloride, which is salt. That is important for living things. The sodium chloride is made of sodium and chlorine, but has different properties. We will be using chemical formulas, such as H2O, to show atoms bonding. It is much faster and easier to use symbols than to write out the entire name. We are going to determine how specific atoms bond together, and to do this, we will use a pattern on the periodic table for electronegativity. Electronegativity is basically how strongly an atom pulls on other atoms' electrons. This is really important because we think of atoms as being neutral, but in order to form a chemical bond, the atoms will either transfer or share valence electrons with other atoms and try to fill their outermost shell. This can result in the atom having no charge, a slight charge, or a full charge. We can see from this periodic table that as you go across a period, the electronegativity tends to increase. Not every element follows that pattern, but for the most part they do. As you go up a group, the electronegativity also increases. So the highest number is fluorine, 3.98, and the lowest number is francium, 0.7. If the atom has a charge because it gained or lost electrons, that means it's not neutral anymore. It's now called an ion, and we write it like this: lithium with a 1 plus charge, sulfur 2 minus charge, aluminum 3 plus charge, or fluorine 1 minus charge. Just like opposite poles of a magnet attract, these oppositely charged ions are attracted to each other and can form a type of chemical bond called an ionic bond. Ionic bonds always occur between metals and nonmetals, with the metals losing electrons and the nonmetals gaining those electrons. A chemical bond with a partial or no charge is called a covalent bond and will be discussed in a different video. This video will focus on ionic bonds, so let's determine if a bond is ionic or covalent. We can determine which type of chemical bond will occur by finding the difference in electronegativities between the two bonding atoms. If the difference is around 1.5 or higher, then it is classified as an ionic bond. If the difference is about 1.4 or less, then it is a covalent bond. Let's try two examples. We can use the periodic table with electronegativities on it to determine the electronegativity values for potassium and sulfur. Sulfur is 2.58, potassium is 0.82. We subtract those two numbers and get 1.76. That tells us that the bond between potassium and sulfur is an ionic bond. We do the same thing to figure out what kind of bond there is between carbon and oxygen. Using the periodic table, oxygen has an electronegativity of 3.44. Carbon is 2.55. We subtract those two values and we get 0.89. That tells us that carbon and oxygen is a covalent bond because it's between 0 and 1.4. Here are 6 examples for you to try. Pause the video. Use the periodic table to determine the difference in electronegativities, and then determine if the bond is ionic or covalent. The answers will be shown after you resume the video. I hope you got them all right, but check your work just in case. Now that we can determine if a chemical bond is ionic or covalent, we can now look at our first example of an ionic bond. This is sodium bonding with chlorine. We know how to diagram sodium. 11 protons, 12 neutrons in the nucleus, 2 electrons in the first shell, 8 in the second, 1 in the third. And for chlorine, 17 protons, 18 neutrons in the nucleus, electrons are 2 in the first, 8 in the second, 7 in the third. So chlorine has 7 valence electrons. It needs 1 more to fill its outermost shell, that third shell. Sodium has 1 in the outermost shell and needs 7 more. Both atoms are pulling on the outermost electrons for the other atom. But remember, chlorine has a higher electronegativity. It's stronger. So chlorine actually pulls the one electron from sodium into its outermost shell, giving it 8 in its outermost shell. Chlorine now has a full outermost shell. Sodium also has a full outermost shell because it lost the one electron in its third shell, meaning its outermost shell is now the second shell, which was already full, so everything works out. It is much easier to draw an electron-dot diagram. The one valence electron from sodium moves over to chlorine, filling its outermost shell. Since sodium lost one of its 11 electrons, it now only has 10, and 11 protons means it has a 1 plus charge. The chlorine, which used to have 17 electrons, now has 18. It only has 17 protons, so it has a 1 minus charge. Remember, oppositely charged ions form an ionic bond. So they move together and form sodium chloride. Here is another example. Beryllium bonding with oxygen. I already drew most of the atom. I left out the neutrons because they aren't involved in chemical bonds anyway, and pretty soon we will stop drawing the atoms at all and just use the electron-dot diagram. You can see that beryllium has 2 valence electrons in the second shell, which is the outermost shell. Oxygen has 6 in its outermost shell. Both atoms are pulling on the other atom's electrons, but once again, oxygen is the nonmetal, has a higher electronegativity, 3.44 versus 1.57. So oxygen wins and pulls the 2 electrons in beryllium's outermost shell into its own outermost shell. Oxygen now has a full second shell, while beryllium also has a full shell. Its first shell is full. We can show this much faster with an electron-dot diagram. The 2 valence electrons in beryllium's outermost shell move over to oxygen's outermost shell. Both atoms now have full outermost shells. Since beryllium lost 2 electrons, it has a 2 plus charge. Oxygen gained 2 electrons, it has a 2 minus charge. The oppositely charged ions attract, and they form a chemical bond. Here is another example, gallium and nitrogen. I'm just going to use electron-dot diagrams with kind of the diagram of the atom up top to help. We can see that gallium, the metal, has 3 valence electrons. Nitrogen, the nonmetal, has 5 valence electrons. Nitrogen, as the nonmetal, has a higher electronegativity and will be able to pull the 3 electrons from gallium into its own outermost shell. It now has a full outermost shell. Gallium also has an outermost shell that is full, but it's the third shell. By losing 3 valence electrons, gallium ends up with a 3 plus charge. Nitrogen gains 3 electrons, giving it a 3 minus charge. The 2 ions are oppositely charged and they form a chemical bond. You may have noticed that in each of the previous examples, the positive ion lost the same number of electrons the negative ion gained. They had the same oxidation number, just opposite charges, like 2 plus and 2 minus. This is not always the case. Let's look at some examples of ions that have different oxidation numbers. Here's magnesium bonding with fluorine. Magnesium has 2 valence electrons and needs to get rid of those 2 to fill its outermost shell. Fluorine has 7 valence electrons and needs 1 more to fill its outermost shell. Fluorine is the nonmetal. It has a higher electronegativity. That means it's stronger. Fluorine is able to pull a valence electron from magnesium into its own outermost shell. In fact, 2 fluorines actually pull each of magnesium's electrons into their own outermost shells. There's 1 magnesium with a 2 plus charge. There are 2 fluorines, each with a 1 minus charge. So those 2 1 minus charges are able to cancel out the 2 plus charge on magnesium. We write it as MgF2. Here's lithium and oxygen. Lithium has 1 valence electron, oxygen has 6. Lithium needs to get rid of that 1, while oxygen needs to take in 2 more. The nonmetals have a higher electronegativity and gain electrons. So oxygen is able to rip the 1 electron away from lithium and start to complete its outermost shell. But it still needs 1 more. So it has to find a second lithium and take its electron and add it to its own outermost shell, giving it 8. There are 2 lithiums, each now with a 1 plus charge. There's 1 oxygen with a 2 minus charge. The 2 lithiums cancel out the 1 oxygen, and we write it as Li2O. Here is sodium and nitrogen. Sodium has 1 valence electron, nitrogen has 5. Each sodium needs to get rid of 1. the nitrogen needs to take in 3. Each of the 3 sodiums and the 1 nitrogen all have full outermost shells now. There are 3 sodiums, each with a 1 plus charge, and 1 nitrogen with a 3 minus charge. The 3 1 pluses cancel out the 1 3 minus, and we write it as Na3N. Here's another more complicated example: magnesium and nitrogen. Magnesium has 2 valence electrons in the outermost shell. It needs to get rid of those 2. Nitrogen has 5 valence electrons in the outermost shell. It needs to take in 3 more. Nitrogen is the nonmetal and will gain electrons because it has a higher electronegativity. It will take 2 electrons from magnesium, but that only gives it 7. It still needs 1 more. The nitrogen will find a second magnesium and take one of its valence electrons and put it in its outermost shell. Now the first nitrogen has 8. It has a full outermost shell. But that second magnesium still has 1 more electron to get rid of. So it will find a second nitrogen and give its electron to that nitrogen. Now the second magnesium has a full outermost shell. But that second nitrogen still needs 2 more valence electrons. It has to find a third magnesium and take its 2 valence electrons. Now all 3 magnesiums have full shells. They lost the 2 electrons in their third shell. That was their outermost shell. Each nitrogen needed 3 more, and each of the 2 nitrogens got 3 more, filling their outermost shell to 8. There are 3 magnesiums, each with a 2 plus charge, and 2 nitrogens, each with a 3 minus charge. The 3 2 pluses cancel out the 2 3 minuses, and we write it as Mg3N2.